Okay, I think we get started. The second lecture, certified Alimohammadi, Stanford University, and the title is Local Algorithms for Predicting Epidemics.
Thanks for the introduction and thanks for having me here. My name is Yeganeh Alimohammadi, and I'm a PhD student at Stanford University advised by Amin Saberi. And today I'm excited to talk about a very recent work about algorithms and epidemics. So most of the infection is spread from some kind of person-to-person context, and networks emerge naturally in the study of epidemics. But how does this network look like will change how does the infection behave throughout the network. For example, if I have isolated cliques of households and one of them randomly get infected from traveling, the rest are safe. But if on the other hand, I have like a party-goer household and they travel and get COVID, all of the town are in some sort of risk. So properties of the network are important, but at the same time, we cannot map the whole network. So the main question we're asking is what kind of information about the network do we need to predict epidemics? And I'll be more precise about the question, but let me first define what's the epidemic model on network that we have. So we are considering an SIR model, which is a very relevant model for infection that bring immunity to the recovered people. Each node or each individual can have either of the three states, susceptible, infectious, or recovered. And when a node gets infected, they're infectious for a time t. This could be random. And while they're infected, they can transmit the disease to their susceptible node at some rate beta. So for example, this first node is infected, and they can transmit the disease to their neighbor, and then their neighbor can transmit the disease to another node, and then all of them recover before infecting more people. And for how long the time that a node is infectious, we can have different choices. For example, t could be a constant, or it could be random, for example, drawn from exponential random variable. That depends on how we want to model the epidemics, but for now, let's just keep it as simple as we want. Is there any question about the model? Okay. So now that we know the model, let's go through a thought experiment. Let's say we have two copies of the same city, and I'm looking at it at day 1 of an infection. I know exactly which people are infected. In both of them, it's the same set of people. But from now on, the infection is going to spread independently in these two parallel wards. And because of the randomness of the infection, how people are, what set of people are getting infected are going to be different. So we can ask different questions here, like in these two set of cities, even if I have the network, can I say what's the probability that an outbreak happens? Or can I say if an outbreak happens, what's the size of it? Or what's the time evolution of these three different components SIR? So now I'm going to run the simulation in both networks, and you see as it grows, while the initial condition was the same, this different set of people are getting infected at time, and even at the end, like the gray nodes are the ones that have getting recovered. You see, like for example, these set of people didn't get infected, but there they got infected. But it seems like the time evolution look kind of the same. Can I say that is true theoretically or not? So to answer these kind of questions about epidemics and network, the traditional approach is a network model kind of approach. What do I mean by that? There are two steps I have to make here. First, I have to choose a random network model to see how the interaction between people go. And I have many choices for that. I could start with like Erdos-Renyi, where there's a homogeneous mixing of people. Any two person can have the same sort of probability of getting connected. Or I could say, oh, that's not realistic. I can introduce super spreaders to the network by looking at configuration model, for example. Or there are also models to like look at the dynamics of network where people come and get friends with more popular people. Or it could be that like I have some data about demographics of people, and based on that, I can see what's the risk of getting infected. And for that, there are like a stochastic block model to capture those kind of dynamics. And in all of these models, there's a problem that I don't have any loops when I look at the network. So there are models to capture that, for example, the household model, to add like loops or local structures to the graph. I'm just saying this long list to say that like there are many choices to make in this first step to just model the interaction between people. And it's not really obvious which of these is the right one. And even after I make that decision, there is a second step that I have to estimate the relevant model parameters after that. What do I mean by that? So let's say I want to, for example, predict the size of an outbreak and I've chosen Erdős-Rényi graph. Then I have to estimate the average degree. Or if I have chosen the configuration model, I have to estimate the degree sequence to say something about the outbreak size. And each of these two steps, I can make mistakes. And it's not really obvious how much my mistake would change my prediction or not. So the main question we are asking here is that, can we have a model-free estimation of epidemics? For example, predicting probability, size of an outbreak, or whole this time evolution without really assuming the network model. And in a nutshell, I'm going to say that under some condition, this is true. Only local information about the network is enough to get the whole time evolution of the SIR process. And you don't need to know the network model. So we are assuming the first SIR process that I told you. And I assume that initially each person have the same chance of getting infected with some probability alpha. This could be very small. But for many general graphs, I can evaluate the time evolution of SIR by only looking at local structures. So next, I'm going to define what do I mean by evaluating the local structures. I'm going to define an algorithm that looks at these local network structure to predict the time evolution. So what's this algorithm? Let's say I have this whole big network. I don't have access to it, but I'm going to probe the network and some information about the network by some sort of contact tracing in a way. So in this algorithm, I draw a uniform random node, and I'm going to see, for example, at time t, let's say a week from now, what's the number of people in SIR. And the algorithm draws a uniform random node and look at this K neighborhood and runs the infection on that K neighborhood and then return the status of V at time t, for example, a week from now. So I said initially each node has the same chance of getting infected. In one example of the run of the algorithm with K equal 4, we see like, for example, one node is infected initially and then it starts. Yeah.
Is that how many iteration K steps? Or?
It's like I do a depth first process until I get to K nodes. But it's not, I will tell you, it's not that important, like how do you define the K neighborhood?
All of radius K. And return the status of V or the status of everyone in the K neighborhood?
The status of V. So like I draw this node V and I look at some up to I get like to K other nodes in that neighborhood. And then one node was infected, I run the infection up to time t. And in this run, we didn't get infected. So I set the status of V at the end is S. So that's what it returns to me. And I can like make few different queries to the network. And each time I get one of the 3 SIR possibilities that I can have. And then one sort of estimator is that I take average of like what fraction of nodes that I saw was in S, what fraction was in I, what fraction was in R, and that's the estimator, basically. So it's, I guess, very simple way of estimating SIR with only local information. So this is like for the case that I want to see a finite time t, but what about I want to see, for example, what happens at the end of the epidemic, what's the size of an infection, then I could change the algorithm a little bit. I could say, oh, like run up to t infinity, but that might be a bit costly. But at the same time, I could say, let's say if I had the network and I pick a random node, what's the chance that that random node is going to be infected at the end of the day? So instead of running the infection forward, I can think of reversing the time and assuming that if the first node that I picked randomly was infected, who has infected it and who has infected their infected neighbor until I see if that is growing or not. So following that idea, I start with a uniform random node. And I see that like in my draw, this node wasn't initially infected. So I see if, assuming this node is getting infected, who is going to infect this node? And I contact trace it in a way. And their neighbor wasn't still initially infected. So I should see if it's getting to someone who is getting infected initially or not. And well, yeah, I get to someone here. So in this scenario of k equal to 4, my algorithm returns true that like my drawn uniform random node is getting infected locally. Let's say I contact trace it up to like level 4, up to getting to 4 people, and I don't get to an initially infected person. In that case, it just returns 0. So these are the very simple estimators for locally estimating the size of an outbreak and the time evolution of an outbreak. And very recently with Christian and Min and Remco, we show that these are actually the right estimator. So for a sequence of convergent graphs, I will define that later. What does that mean? Just get it from me that like most of the network model that you can imagine satisfy that condition. A constant number of queries with a constant k is enough to get the final size of an infection from the last estimator that I showed you. And also from the first estimator with a constant number of query and a constant k, I can get the time evolution of SIR. These are assuming that initially alpha fraction of people getting infected, but I can also take that alpha to 0, and still these estimators are the right thing to look at. A few notes about the algorithm. First of all, the way that I'll show you, maybe it's not very immediate to see it, but it can be implemented in O of 1. Even the first algorithm, I could implement it in O of 1, even if I have a few nodes of large degree nodes. I could just do it backward in a sense. And it's model free, of course. I didn't assume anything about the network, and it preserves edge differential privacy. So if I care about not revealing information of edges, that's fine. And it's extendable to dynamic networks that nodes can come or remove from the network in some sense. And it doesn't require anything like local tree like a structure, which is implicitly assumed in many of the network model ways of studying this kind of model. So if there is no question, I want to now change the initial condition. So far, I've been assuming that like alpha fraction of people are infected initially, but let's say it's very early stages of COVID, and I want to see what happens if one person has traveled from another country to the US, how would the infection go? And that's a very different kind of question, because when only a few people are infected initially, there is a whole stochasticity going on in the beginning that I cannot really predict it. And it's not just that, like as you can see in this simulation, even after the beginning, there is a whole randomness in how the I curve looks, for example, in these two graphs. So maybe I cannot wish for constructing these whole SIR curves for general graphs, but maybe I can assume something about the graph, which is not the network model, but some global structure that can promise me local algorithms are enough for estimating outbreak size, for example. So another example why local structures aren't enough, because I can construct two different sets of graphs that have the same local structure, but different outbreak size. So on the right, I have a 4 regular random graph on size n. And on the left, I have 4 regular random graphs of a smaller size. And locally, they look like the same. But if one person here gets infected, many others are getting infected, and one person getting infected, they're only log n people are getting infected. So I can't even say anything about the outbreak size, let alone the whole SIR process in these two graphs. So here, we assume that the network, if the network is well connected enough, and if I simplify the random process of the infection a little bit, I can still estimate the relative size and the probability of an outbreak with local samples. So here I'm assuming a simple epidemic model, meaning that the recovery time is a constant. It's not random as it was before. And I'm defining the outbreak as the event that omega n number of people, super constant number of people getting infected. And then we said that the probability that this event happened and the size of an outbreak as a result of it is has a local structure. So far, I haven't give you an estimation for a probability of an outbreak because before alpha fraction was already infected. So what would be a natural estimator for the probability of an outbreak? Still, I have this whole network that I don't have access to it, and still I want to draw one uniform random node and look at local structure. But instead, now I assume V is the first patient and see if that person is going to infect many people or as I want or not. So locally, with k equal to 4, I start infection from V, and I see that it doesn't lead to infecting 4 other people. So in this run of the simulation, I say I return 0. But if V could infect 4 other people, I would return 1 and say, oh, V is like probably leading to an outbreak. And then as a natural estimator, again, I can make a few queries of this algorithm and take average over the result. So far, I have told you an estimator for the time of evolution, for the outbreak size and outbreak probability. But it turns out that if under the conditions that we have, under the infection model that we have, the probability and the size of the outbreak are the same on well-connected networks. So with Christian and Amin, we proved that if we have a sequence of well-connected graphs, and I will define that more formally later, then the final size of an infection is a 2-atom random variable. So the relative size of an infection converges to a random variable that's either 0 or some constant of p, where p is the transmission rate. And we see that this random variable, the constant p, appears with the same probability zeta p. So that's not random. That says that the infection relative size is the same as the probability of an outbreak that happens here. So the big takeaways of this is that the final infection size with high probability is either constant or zeta p times n. And the probability and the size are the same with constant recovery time of SIR. So now that we know this information, the second part of the result is that the estimator that I showed you about the probability is actually the right estimator to approximate, give a one-minus approximation of the relative size and the probability of an outbreak. So if there is no question, you can have question.
Could you say something about how large these constants are and as a function of the parameters?
That's a great question. I can say something about how Q can be large. That just comes from some Chernoff one. So it goes, I guess, relatively fine with epsilon. But how K, or like this local neighborhood grows with epsilon, depends on the graph limit, which so you can just run the simulation and see when does it converge, but I don't have a convergence result. I will show you some simulation results for some music.
Does the fact that there is an SIR model underlying this, is this important, or you could go model free with respect to the transmission process too?
Yeah, you can change the transmission process as long as it has some wide conditions.
The constant infections, which makes infections independent, isn't that assumption?
For this result, yeah, I need the independence between the infection rates.
So the network essentially is static, right? You're not changing the beta, for example, the transmission rate is constant throughout the duration of the.
Yeah, those are our grade scores to see like as further work, but we don't know what happened as better as
How large?
Yeah. So now if there's no question about the result, I go to what are the conditions that they need to work.
I have a comment, which is if beta changes with time, you cannot do that.
Yeah.
But if beta would be different on different edges, we could still do it if it has certain regularity.
Oh, I see.
So now about the conditions that we need. First, I want to go over the convergent condition. So this is actually relating the results of graph limits, which is, I guess, one of the main topics of this whole program. We say a sequence of graphs in a high level have like a limit if the distribution of a typical node, of a uniform random node, converges. So what do I mean by that in an example, in a simple example? Let's say I have this kind of grid and I'm growing the size. And I have two kinds of nodes here, either the green ones or the blue ones. And if you look at the green nodes, all of them have degree 8 and their neighbors have degree 4. Their neighbor have degree 8 again. So if you look at them locally, they all look the same. And if you look at the blue nodes, they all look the same. So a uniform random node with probably half is green, with probably half is blue. So this sort of graph is like having a limit. But this is a very simple example of graphs with limit. And we see a lot of many more examples in the bootcamp, including a few of them that are very relevant network model. For example, Edershreni and configuration model that have a branching process limit, preferential attachments or household models. You can define, I guess, any kind of network, any kind of easy network model have like some sort of limit in a sense. So getting to the second condition, which was well-connectedness or expansion. So a graph is an expander if you want to remove a set of nodes S from the rest of the graph, then you have to remove linearly as many edges to disconnect it in some sense. And you actually need a weaker condition of this sort of expansion, meaning that I only need to have that condition on a set of size S that have linear size in N. So I could have potentially a few disconnected components, but as long as sets of linear size in N are well connected to the rest of the town, then it's fine. So I guess any single town that you assume, for example, Berkeley is expander, I guess. But maybe if you look at the union of Berkeley and I don't know, Cornell, maybe it's not. So examples of a few converge and large set expander, meaning that a few graphs that satisfy all of our conditions for our second result are configuration model, preferential attachment models, and household models. And I've said the household models a bunch of times, so tell you what is it like in a high level. You can start with any sort of graph that you want, and then you can blow up the vertices with any local structure that you want, as long as it's connected and the size is bounded, then you're fine. So that's like you're introducing households instead of like that green node, you're introducing a household of 3 people. So this kind of network model allows you to introduce any local structure that you want. And as long as the external graph has the conditions that we need, like expansion and convergence, then after you blow it up, it's still like it has the condition that we need. So you can apply our local algorithm to get outbreak size on them as well. So before getting you to some proof ideas, let me show you some simulation and real data. So here we are looking at Copenhagen dataset, which was a data set for flu epidemics in 2019. They tracked the students' GPS data, and it has like around 100 nodes, and we put edges if the distance are within 6 feet within like half an hour or so. And here I'm actually answering the question that Suraj had, how large should be K? So I want to be like, how large should be K to, for example, estimate the probability of an outbreak. When I start with K equal to 0, almost exactly always like the first node is infected. So I'm overestimating by far, it's like probably 1. But as I increase K, when I get to 3, then it's almost very close to the real probability of an outbreak. So you don't really need to like grow that K a lot high compared to the whole network size. So if there are no questions, I get to some high-level proof ideas about the last part of the results.
Yeah, it's K actually. I'm not sure what does K really mean. What is K? We said K is like infection for other people. One K is infection for others or for neighborhoods. Is that a production number in your simulations? Or?
No, it's not the reproduction. So here, like the transmission rate is like 12.28 almost, yeah. This K depends is kind of saying how much knowing the local structure, how far going deep into the graph is enough or not. So if you want to, for example, if I had, let's say in a contact tracing board, I had access to uniform random samples in a board, then I only like contact it. When I see an infected node contact tracing up to like 4 people, that's enough for me to say something about what would be the size of an epidemic if it goes on.
So K equals 4 doesn't mean I've infected 4 people. No.
Eventually,
No,
I
it's
get
a generation.
it's a generation.
So
For the
once you observe 4 generations,
okay.
you get a very good estimate for
Nice.
the final outbreaks.
Very good, very good.
Any other questions?
I have another related question. So here you show how the approximation behaves with respect to K.
Yes.
CP to find K, like if you have data?
Not yet, but I would just like run the infection to see where does it converge. But that's a great question to study later to see what would happen as K goes. Any other questions?
So if I think of these as subgraphs around that node B that you're picking, these are all tree subgraphs
No,
or they're chains.
no, they could be anything. Actually, that's the point of our result.
But you're not seeing how, for example, so if V connects to X and Y, you're not looking at X to Y, or you're also looking at
Yeah,
X has
yeah,
connection
yeah.
to Y.
Maybe my yeah, I'm looking at that too.
You're looking, and that is counted as part of the query, or no, that's not counted.
So the query doesn't return to me the whole structure. It just tells me whether it reached K other people or not, and it doesn't matter if it goes through a loop or not.
Right, but doesn't that count as a budget? Because you have to then, in a way, you are querying whether X had contact with Y.
I'm not sure exactly what's the problem.
Well, we can talk afterwards, but what you're telling me is that if I pick a V and I'm doing this querying, I don't necessarily get a tree. I can actually get something that's more expressive than a tree.
Yeah, so like this whole algorithm is a black box for me. If it doesn't get a tree or not, doesn't matter. It doesn't tell me what it gets. It just tells me whether it's eventually getting to K other people or not. That's what it returns. So yeah, so it could be a triangle. It starts from V, gets to X, and X gets to Y, or it could be Y is already like getting affected from V or not. So like, we can talk later.
So this red line seems to be around 0.18 or something.
Yes.
Is my interpretation correct that is if you, for this given data set, random node and let the epidemic spread, and you see was it a big outbreak or not, and you repeat this 10,000 times, we
Yes.
get the big spread in 18% of these.
Yes, that's the exact. That's the way I got this like truth value.
And how did you find big? Was that bigger than 5%, or what was your definition?
What's the outbreak size? Yeah, you can define it as 5%, but I guess in this data set also it's well connected enough so that if it gets to 5%, it gets to more than like the final. It's always like this final size of outbreak. That's I don't know what was it here. I guess around 50%, but.
One more question. I'm surprised at the confidence interval. Why doesn't it narrow down the bigger K?
So here the confidence interval depends on the number of queries, not K. I fix the number of queries. I always query 10 times. Like I'm always contact tracing 10 people in some sense. If I increase Q, then I narrow down the confidence interval. That's a good question.
And this is a scenario where there's no intervention whatsoever going on.
Yeah, there's no intervention.
This is the spreading over.
Yes.
Very good.
So is there are no more questions, I can get to some high-level ideas. So when we have SRR with constant recovery time, it connects to some very well-known notion for mathematicians in some sense, which is called percolation. In percolation, I keep each edge with the same fixed probability P, and I call that G of P. And one can show that SIR with constant recovery time can be coupled to this kind of percolation. So instead of looking at outbreak size in a dynamic infection process, I can look at the largest component or the giant in this corresponding G of P. So the next goal is to see what would be the size of the giant in G of P, which I'll show you in a slide. So we showed that under the same sequence of graphs, like well-connected converging graphs, the size of the largest component over n always converges to a fixed number, which is actually the size of the outbreak in our epidemic notion. And the second largest component always converges to 0. So what we showed is that the largest component is unique, the size converges, and in some sense also we can estimate the thresholds where we have like a large component or not. So how can we show the size of the largest component converges? Pictorially, in a very high level, I can bound the relative number of nodes in the largest component with 2 values that I can easily say those 2 values converge. So the upper one is actually kind of easy. So instead of looking at the relative number of nodes in the largest component, I look at the nodes that appear in a component of larger than k. This k is actually the same k of contact tracing I was telling you. So everything that appears there actually is in a large component as well. So that's the upper bound. And as a lower bound, instead of looking at G of P, I lower the transmission rate with some epsilon, P of epsilon. And then I look at the nodes that appear in a component larger than k in this new graph. And this lower one is actually the hard part to prove, which we use a very well-known technique of sprinkling here. If I show like these 2 bounds are the right bounds, then I can show that these quantities, the upper bound and the lower bound, are both local. So like they only depend on this k structure, they both converge. And then I need to show that this zeta k, like this p minus epsilon quantity and the p quantity are very close. So I need to somehow show that like there is this zeta is a continuous function of p in the sense of an epidemic. That means that if let's say I didn't know this true probability of p and I was estimating it and I had some error, but that's fine because this outbreak size or outbreak probability is a continuous function of that p. So if I have like a good estimate of that, that's still fine with me. And so now maybe for a few minutes, I get into more detail of like how does this sprinkling look like here. This is actually, as I said, has a very long history going back to Erdos, and many more people have used it that I haven't listed here. And the idea is basically that I was looking at this infection process with transmission rate p, but instead I lowered it, as I said. So I have this original graph. I have the graph with probability p1. P1 is less than my original infection rate. And I add back that probability epsilon to it such that if I look at the union of Gn of p1 and Gn of epsilon, the probability that an edge appears is the same as the probability that an edge appears in G of p. So the same transmission rate. And I want to say that any sort of component of size k here will attach together with these orange edges to create a large component here. So that's the basic idea. And if I want to get to more detail, as a second step, I have to show that there are linear number of nodes that appear of a component size larger than k. And then I have to say that if I look at the unions of components of size larger than k, like if I can separate them in 2 sets of A and B, the probability that they're not connected is actually very low. They're not connected in this like orange graph. And then if I say all of these steps, I can say that I have like a large component of linear size. So I can get into more detail of these like step 2, but I just go very fast, I guess. The idea, like the very combinatorial idea, is here coming from some theorem called Menger theorem. It says that if I have a well-connected network and I look at 2 large sets of size of A and B, and I know if I want to disconnect A and B, I have to remove many edges. This theorem says that because of that, there are many edge disjoint paths between them. So like, what do I mean by edge disjoint path? For example, the green path, blue, and the orange don't have any edge in common. And why do I care about that? Because if I add them back with probability epsilon, I want those to be independent in some way. So this kind of theorem allows me to like say that if I have these 2 sets of large A and B in my original P minus epsilon graph, after I add back edges with probability epsilon, with high probability, one of these paths is going to appear. And I can then take the union bonds over all of these sets and say that there is no way to partition A and B. So these are getting very nitty-picky, but I guess going back to the main takeaway of the talk, local information goes a long way. So if you want to predict some global property like probability of an outbreak or the size of it, you can only look at these local structure of the graph, especially if alpha fraction is infected. You don't need to really assume anything about the network structure except this convergent condition. And if you start with one node, then it's more complicated and we need some sort of expansion or some sort of well-connectedness to say something about the outbreak size. And all of this has been enabled for us because of graph limits. Can we find more application of these graph limits or not? And with that, I thank you and I'd be happy to get one
question. So in like property testing, often it sort of starts with one graph model, like a dense graph model, and then it's, a fixed degree, and then people go and they do results about general graphs, depending on what the question is. So, does this mean sort of more generally as an approach where you could say, forget about modeling what the graph looks like, maybe we can solve problems and find out maybe what the graph looks like and then adopt. You're not finding out the graph looks like, you're just asking specific questions about specific nodes. Mm-hmm. Whereas I guess in property testing, you want to know about some property of the whole graph. Mm-hmm. So you want to know about a global property from local information, but usually you assume that the graph is a particular.
Can you use the microphone so that people online can?
I can repeat the question.
This is my question.
So I guess I just repeat the question for the virtual.
Okay, I can just say. So all I'm saying is that I was thinking about property testing, where often so you want to know global property, but you want to find it out with local information. But almost in all the results I know about, which grant you is when I was doing this was a while ago, is that you assume one graph model. Maybe it's a dense graph, then it's the constant degree, then maybe other models, and hopefully eventually it's for general graphs. So your approach seems to say, at least for local answers, not for global answers, that maybe you could just sort of search what the graph looks like and then adopt, I don't know, one approach or another.
Right.
I was just wondering if that's something people do. Maybe they do. I don't know.
That's a great question. I don't know. I haven't looked into it to see what's the answer, but I guess it has a potential to like look at this local structure and say something about the global property of the graph. I guess that's a very great question to look further into.
Are there any more questions? We have plenty of time.
Sure. You talked about regime. Oh, is it?
Yeah.
So you talked about two regimes of having alpha fraction or one. Any comments or anything in between? in terms of initial?
I guess the in-between condition is when alpha goes to 0. And so like we still have our result still applies. So when alpha goes to 0, this is the first result.
What is the rate, or does it matter?
No, it doesn't matter if, yeah. So I guess if it doesn't depend on n, it's fine. Yeah.
Okay, I should give you the microphone so people online. That's okay, no worries. I need the exercise.
So I guess I was wondering if we had a really big graph, is there some sort of way that we could get a sense of whether it's well described as a graph limit, and we could try to apply these things to it?
That's a great question. I guess maybe Christian has a comment on it, but I think so the question is that if we just have a fixed graph, can we say it's well described as a graph limit or not? And I think we don't know theoretically if we can describe just a fixed graph as a graph limit or not. But I guess morally, these kind of methods apply to it as long as like local structures of random nodes have some sort of value distribution.
So you had a slide where the sort of the theorem was stated. So I don't know networks and graphs as well as you guys do, but it was a sequence of large set expanders with bounded average degree converging locally in probability. So that, I guess that somehow formulates what is necessary for the network to have sort of some stability as you send, but for people like me, is it possible to explain sort of in, I guess it means that as you look at the larger network, picking a random local structure, it should sort of stabilize as n tends to infinity. Is that more or less what it means? Or?
The convergence part is more or less what that means exactly. So like I need to be that the typical node is because the structure has like some distribution. So if I look at the empirical distribution of local structures, though that's like convergence. But about the expansion of
All the random models you ever look in your life at.
Yeah. And then about the expansion part, that's like just ensuring that like I don't have two disconnected community in some sense. And it's still like many of these random graph models like configuration model, preferential attachment, and household model have that property.
I think the result you have has already been proven for those three examples, but I guess your situation is much more general.
Exactly.
So the interesting thing is when you go outside of those models, because I think the results already existed for those three models and many others, but you have a more general situation.
Yes, exactly.
Thank you.
Questions? Yes, sir.
It's just a like practical question. So can I interpret your results as for the next pandemic, let's choose like QE, your QE number of groups. I am the government, I pay them to give me all the information and test regularly. And as long as I monitor those households, call them, or groups, I can have good estimates about the world or like my country.
Well, you also have to pay them to volunteer to get infected.
Oh, so I see what you're saying. So I have to initiate the infection too.
If I have the transmission rate, I can simulate the infection. But yes, I guess that's the takeaway.
Exercise.
Somebody on that end.
Oh, okay. Excellent talk. So I know that you don't know the leading eigenvalue of the adjacency matrix, but what is the relationship between K and that leading eigenvalue of the adjacency matrix?
I haven't looked at it yet, to be honest, but that's a good question to look further into. Thank you.
The leading, I'm glad we're
Probably
talking.
not related, yeah.
Are not really related to that, but not related.
But
Maybe
it
the
should be,
expansion too.
right? But it should be. Because the leading eigenvalue of the adjacency matrix tells you about the path capacity, tells you about how many different ways this line is spread in the network.
Same with R naught, right? The spectral radius of the next generation matrix.
It's not more than R naught.
Jorge, you have a question? Okay. Any other question? Joel? I can ask a question. Okay, let me ask a question quickly. So my understanding is you're saying, okay, in this situation, we just local information is all we need to characterize and to be able to realistically estimate the final size of an epidemic. But suppose I'm looking at it from the point of view of, let's say we have a meta population model where the total population is split into multiple patches and the patches are connected by mobility. So if I'm in patch A, and so to characterize what's happening in my patch, I just need to focus on my patch and not any of the connected patches. But sometimes what's happening in other patches has a non-trivial consequence in what's likely to happen in our patch. So how do you extend, or can you speculate if you have a meta population structure? Would we still need just the local information, or we also need what's happening? For example, in one patch, maybe a lot of people are vaccinated or observing quarantine, but in other patches not. What's the impact of that kind of structure, meta population patch structure, on the results that you have?
That's a good question. I think in the first set of results, if I can still say that meta population structure has some sort of limited distribution on the set of the graph, then still I can say something with this local information. But if they are very heterogeneous, I don't know if like one patch is all vaccinated and the other is not, then maybe I should study them separately and like.
So if, for example, you're doing transportation modeling, like people coming in, like the US from many different countries. So we focus more on what's happening here, but not necessarily people coming from other patches. Well, that will not affect the final size of the epidemic. It's just the final size is determined by what's happening here rather than how many people are coming in from other patches or other countries, whether there's a large number of infections in those countries or not.
But it can affect the final size here too because of this transportation. And so like saying about what our local result can do, as long as I have samples from both patch, maybe I can say something.
Okay, good to know. Any other question? We have 10 minutes, so I have plenty of time to ask as many questions. This is so exciting talk. I like it. The what? we can do that, yeah. But that's against the law to enter minutes. Yeah, we have to wait until. No, it's so exciting. It's very nice. But if there are no questions, then let's thank. Oh, sorry, that's a question, Tom. Yeah.
So if you think about, you had a fixed infectious period, and if you have a random infectious period, then of course the possibility of infection, your friends will become dependent. Did you? So
what do you mean by a random?
Well, if I have 4 friends and if my infectious period is random, then the probability that I infect, let's say, you and Christian will become dependent because if I have a long infectious period, it's more likely that I infect both.
Yeah.
But you said you.
That's exactly the first set of results. So if I assume that like, oh no, it's not. This is not the first set.
If I remember
correctly, if I assume that alpha fraction is infected initially, if I assume something about the initial condition, then here this is assuming the general SIR. It's not a constant recovery time. It's a random recovery time. Then I can say this local information or not.
But when you started with one person, you excluded that case. So my question is, if you want to include it, what was the problem that sort of, why did you exclude that? What was the?
I see. Why we looked at the simpler.
Well, I mean, I always do that. If I can't solve a problem, which happens most of the time, then I go to simpler situation. I always do that. So but what was the complicating factor, let's say?
I guess when, that's a great question. I guess when we have this independency, we can look at the percolation. We can think of infection as an undirected network instead of looking at all the transmission because of symmetry. And that makes the study a lot easier. And we couldn't yet, that's our first, like that's our next goal, to see what would happen if we have these, the actual SIR model with like coupling on the expanders and one infected, and what would happen. But yeah, we don't know yet. That's.
She actually discovered So when we were working on that, obviously we first wanted to do what you said. Yeganeh discovered two problems. One of them, if the graph is locally tree-like, we didn't quite know how to prove it in this generality anyhow, but there one might have some hope. It's still difficult, but the main problem is actually if it's not locally tree-like, then actually it's very hard to understand this process, because once you start to get sort of two ways to a node, and even if you condition, that you lose all kinds of independence, which make it very hard to analyze.
If it's tree-like, it should be possible, but much more complicated.
Last one probably. So the SIR, is it epidemic SIR or endemic SIR? Is it for like a brand new disease, or you do not include the demographics, the birth death process, or is it for a disease that has been endemic, has established itself? In which case now you have this inflow of new susceptible people into, because if it's epidemic, then the disease will run out eventually of hosts to infect, right? Because you don't have any influx of.
I guess the way that you're defining epidemic and endemic, it's probably epidemic, because I'm looking at the fixed static network that the disease will eventually run out of.
Oh, okay, so it's epidemic. Okay, excellent, very nice. All right, let's thank Yeganeh one more time for fantastic presentation. Very nice, well done. All right, I think it's now lunchtime, 5 minutes before lunch, but we start lunch early.